Hello everyone, I'm Ziad and I'll be explaining Hemodynamics 1, Chapter 14 P8. So let's talk about the functions of the circulatory system. We have three functions or three cargoes the circulatory system transports. So the circulatory system has, it transports nutrients, transports wastes, and transports hormones. Now for the rate of blood flow, it's controlled by the need of tissues for nutrients. Let's say, your skin is in need of oxygen, then blood flow increases there and it gets the oxygen that it needs. For other organs, for example, let's take the kidney, the blood flow that they receive is much more than metabolic rate. So, not every organ gets the exact blood that they need or the exact supply of what they metabolically require. Some of them, like the kidney, get more than that. Okay, so let's look at the question on the right. What controls blood flow to tissue? Is it their size? Is it their epithelial, they receive more, or is it their metabolic need? Now, obviously, the blood flow is controlled by the need, so it is their metabolic need. All right. Now, to continue on the functions of the circulatory system, we have the blood flow. Now, the blood flows at a rate of 5 liters per minute. And does that number ring a bell? That's exactly the cardiac output. Okay, so the blood flow, it moves at same rate as the cardiac output rate. We have here the aorta and the arteries. They transport blood to tissue under high pressure. So the aorta and the arteries, they're specialized to transport blood under high pressure. High pressure such as 100 millimeter mercury. Now, this 13% that you have next to the artery is how much of the total blood volume or total blood in the body that is in the structure. So, in the arteries, you have 13% of the blood. In the arterioles and capillaries together, they have 7%. Now, the arterioles, they are the control site of blood flow. This is important to focus on. They're the control site of blood flow and they're the major resistance site of the circulation. So if I was asked, if you were asked to, what is the control site of blood flow, you should be saying arterioles. If you were asked what is the major resistance site of the circulation, you should say arterioles. Now, furthermore, we have the capillaries. This is the same 7% that I chased with the arterioles. Now, they're the major site of water and solute exchange, okay, between blood and tissue. Basically, water as in, osmosis and solute as in nutrients. Here we have the veins. They take 64% of the total blood volume. That is why they're called, they serve as a reservoir of blood. They have most of the blood in them. They also return blood to the heart under low pressure to the right atrium, and they have really thin walls. Now let's talk about pulmonary circulation. It has 9% in it. Now the pulmonary circulation is the site of oxygen and carbon dioxide exchange, basically gas exchange. And here I just tell you that the percentages there, how much of total blood volume is in every structure. Now let's take total cross-section area. Let's say, the capillaries, it's kind of in a network, joins here, goes here. As you know, this is just a rough sketch, obviously. And then they join again. Whatever happens here happens here. Now, if you were to cut that in the coronal section, you'll get something that looks like a circle or looks like, you'll get a shape out of that. And then the area in there, that's the cross-section area. That's the cross-sectional area. If you add the area that you get here, and the area that you get here, and the area that you get here, that would be the total cross-sectional area. It is basically the sum of all cross-sectional areas of that structure. Now, for the aorta, you have one aorta. You cut that, in the coronal section, or not even coronal, it just has to be, through it where you get a shape. Depends if you're cutting like the descending, then you'd be going in the transverse, and so don't think about the in which plane you're cutting. Think about the shape that you're getting out and how many of that you're getting. For the aorta, you're getting one shape, and that shape is gonna be 2.5 centimeters square. That's the area that it's gonna have. Now for the small arterioles, all of them, all of the cross-sectional areas that they have is gonna sum up to 20. And then arterioles are just gonna be, double that, double that of the arterioles. Now here capillaries, you have plenty of capillaries. So it makes sense for the capillaries to have 2500 as their, cross-sectional area. It's 1,000 times more than that of the aorta. Aorta is 2.5, capillaries are 2500, that's 1,000 times more. Then we have venules, that's 250. We have small veins, that's 80. Then we have the vena cava, which is 8. The venous system has a larger blood capacity than the arterial system. So the veins, they have more blood in them, they, have more space for blood in them than the arterial system. Now let's talk about the blood velocity. The velocity of the blood is the speed of the blood flow in the circulation. So how fast the blood flows in the circulation, that's the velocity of blood flow. Now, the velocity of blood flow, let's have that as V. It would be equal to the blood flow itself, let's have that as B, or let's have that as F, as in for flow, divided that by the cross-sectional area. That would be the velocity of blood flow. So, the more you have, more cross-sectional area, you'd have less velocity. More blood flow, you'd have more velocity. Okay? So, since aorta has what? 2.5 as its, cross-sectional area. Okay, that's bad handwriting. My bad. 2.5 2.5 whatever, 2.5 centimeters squared as its cross-sectional area, then it would have the most velocity, it would have the highest velocity of blood flow. It would have the exact number of 33 centimeter per second. Arterioles, they're a bit slower, but they're faster than the small veins, and the capillaries are even slower because they have the highest cross-sectional area, which is 2500 centimeters squared. So it would be in the speed of 0.3 millimeters squared. Focus on the units, they might, check you with that in the TBL or in the final exam. Now, let's talk about the principles of the circulatory function. Now, we stated before that the blood flow is controlled by what the tissues needs. So, what are the needs? We have the oxygen, nutrients. If let's say it has too much, waste products, it's gonna need blood to take it out, and maybe hormones affect that. So, central nervous system affects that as well. Then we have cardiac output. Cardiac output is controlled by what? By local tissue flow. So, blood flow, it's controlled by what tissue needs. Cardiac output, as CO, it's controlled by local tissue flow. We have two things here. We have automaton and then we have special nerve signals to, increase the cardiac output. So special nerve signals, basically you contract the muscle or whatever you do, it basically sends a signal that tells you let's increase cardiac output. Okay? Now for the automaton, it's basically the pumping of blood from the veins to the arteries. What happens is that the veins, since they're the reservoir of blood, they contract or constrict, the smooth muscles in them, they contract, and that just sends the blood and increases venous return, which, at the end increases cardiac output. We have here arterial pressure. It is independent of the blood flow. Arterial pressure does not depend on the blood flow control or the cardiac output control. It's a whole other thing. So if I were to ask you, does arterial pressure depend on the blood flow control or cardiac output control? Answer should be no. Now, low arterial pressure, it causes a bunch of reflexes. Let's talk about the reflexes now. If you have a fall in arterial pressure, what type of reflexes would they have? First of all, heart rate would increase. That's pumping activity. It would help, bring that pressure back up. We have the venous constriction. So the blood gets pushed to the right atrium to increase the venous return. Basically, the veins, they constrict the smooth muscle and then they, contract. And then we have the arterioles themselves. They also constrict to do what? To accumulate the blood in the arteries. These three things, 1, 2, 3, they all help increase the pressure. By the way, this is the TBL objective. To know how, the reflexes work in arterial pressure, fall in arterial pressure. You have to know that. This is very important for the TBL. This is the TBL objective. Now, pressure flow and resistance. Blood flow is determined by the pressure difference, not pressure difference. It would be F, which is blood flow, equal to change in pressure divided by the resistance, the vascular resistance or resistance. This is Ohm's law. Okay, so blood flow is the change in pressure divided by the resistance. As you can see here, change in pressure is P1, P2. Focus on change in pressure or pressure difference. It's not pressure over resistance. No, it's change in pressure divided by resistance. Now, blood flow. What is blood flow? I've been saying blood flow, throughout, the beginning of the session. But blood flow is basically a quantity of blood at any given point in the circulation in a given amount of time. So you can just think of blood flow as quantity of blood. Now we have here the unit of blood. What is it measured in? It's measured in liters or milliliters per minute. So it would look like something like this. One of these two. These are the units. Then we have the cardiac output. What is the cardiac output? The cardiac output is the overall flow in the circulation of an adult. It is measured at 5 liters per minute, and that is the cardiac output. So, overall flow is the cardiac output. Now, let's do this. This is a question. Low arterial pressure. What does it elicit? What reaction does it elicit? Now, we mentioned that the first one is basically heart rate increases. So, pumping activity. So, obviously, decrease in heart rate is wrong. Two, we said that the venous constriction to increase what the venous return. So, dilation of the venules or veins or anything, that's not going to work. Then we have the third one, which is constriction of arterioles. That is gonna accumulate the blood. Now, excuse my bad handwriting, but that is gonna accumulate the blood in the arteries. So obviously, this one's the correct one. Ventricle, prolonged ventricular diastole has nothing to do with this. Now let's talk about blood flow. We have two types. We have laminar blood flow, and then we have turbulent blood flow. In A, this one, A, there is no blood flow. You can basically forget about it. You're not gonna get a question about no blood flow. In B, you have laminar blood flow. It has parabolic velocity. That means what? That the center has much higher speed than the periphery or than the sides, the edges. Due to what? Due to the resistance of blood vessels. So due to the resistance here, you're gonna have a faster center and slower, edges. Now in C, what do you have? You have the turbulent flow. Turbulent flow is a whole other story. Now, as you can see, the direction of the arrows or direction of the blood, it's making whirls here. These whirls, they're called what? Eddy currents. What causes eddy currents? High resistance, which, it's basically higher than the ones in laminar flow, but that's not the only reason. Let's go to the reasons of why turbulent flow exists. So, if the blood is going at high velocity, you're gonna have turbulent flow. If you take sharp turns in the circulation, you're gonna have turbulent flow. If you have rough surfaces, that means more resistance, you're gonna have turbulent flow. If you have rapid narrowing of blood vessel, that's also gonna be more resistance, you're gonna have turbulent flow. So basically, two of the reasons, they're related to resistance, which we said here, high resistance causes it. The other one is sharp turns and high velocity. Now, what is turbulent flow bad? Is it normal? Now, it's normal to some sense it's normal, but it could cause pathologies. What are the pathologies? They increase wall stress, which leads up to aortic aneurysm and atherosclerosis. You don't need to know what these are, but you need to know that turbulent flow causes them. Let's go to blood pressure. Blood pressure is the force exerted by blood against a vessel wall. It is measured in millimeters mercury, which means that the pressure is enough to push mercury for that distance. So if it was 10 millimeters of mercury, 10 millimeter mercury, then you'd be able to push the mercury 10 millimeters. Now there's also another unit, which is of water, millimeter of water. It's used for very low pressures. It's not usually used in the body, but 1 millimeter of mercury is 13.6 millimeters of water. Now, let's talk about the resistance to blood flow. Resistance is, something that delays blood flow. It's the only force that goes against blood flow. Not the only force, but it's a force that goes against blood flow. Now, the equation was F equal delta P over R. If you were to calculate R, you just have to, switch the equation like this. So we're using the same equation. R is the change in pressure divided by the blood flow. Now, what is the unit of resistance? It's PRU. What does it stand for? It stands for peripheral resistance unit. And total peripheral resistance is 1 PRU, 1 peripheral resistance unit. TPR can be 4 PRU. It ranges from 4 PRU to 0.2 PRU. 4 during constriction, 0.2 during dilation. Now, for pulmonary resistance or pulmonary vascular resistance, it's gonna have 1/7 of the total peripheral resistance, in this case 0.14 PRU. Now let's look at this question. 1 millimeter of mercury, this should be G small, is equal to what millimeter of water? Is it 11.6, 12.6, is it 13, is it 14? Now this is kind of just, memorizing. It's gonna be 13. Now let's talk about conductance. Conductance is the measure of blood flow through a vessel for a given pressure difference. So basically it's the measure of blood flow for a given pressure difference. It is equal to 1 over the resistance, so it's like the reciprocal. If resistance increases, conductance decreases. Let's have here resistance up, conductance down. Resistance is down, conductance will be up. It is also proportional to the diameter to the power of 4. So what does that mean? If the diameter is 4, then the conductance is 4 to the power of 4, which is 256. Let's talk about Puzzle's law. We have here rate of blood flow. This is pi. We all know pi, that's 3.14. And then we have delta P. What's that? That's the pressure gradient. This is the same as pressure difference or change in pressure. Just, they put the word gradient to make it sound more fancy. Then we have the radius to the power of 4. This is why it is proportional to the diameter to the power of 4. This part of the equation is what tells you that it is, it relates to the diameter to the power of 4. And then we have 8, just a number 8. And then we have the viscosity of the blood, and we have the length of the vessel. So, if we increase the length of the vessel, we're gonna decrease the rate of blood flow. If we increase the viscosity of the blood, we're gonna decrease the rate of blood flow. If we increase the change in pressure, notice how it's not pressure, like overall pressure. If overall pressure changes, nothing's gonna happen to the blood flow. But if the change in pressure, gets higher, or the pressure gradient becomes greater, then the rate of blood flow is gonna become greater as well. Now, for the radius, as it becomes greater, the rate of blood flow is gonna become greater as well. Now, let's talk about hematocrit. Hematocrit increases the viscosity of blood. So, as hematocrit increases, the viscosity increases. From this equation, you can conclude that the increase of viscosity decreases the blood flow. If N with a weird nose, okay, increases, F is decreasing. What would that lead to? That leads to an increase in vascular resistance as well. So, the increase in vascular resistance over here, it's gonna decrease blood flow and conductance. Alright? So, again, hematocrit increases, viscosity of blood increases, it decreases the rate of blood flow and decreases the conductance. Now, when is conductance higher? Now, here we have a parallel arrangement of a vessel, whatever it may be. The conductance is going to be higher in it because the resistance is going to be much lower. It's going to be C total equals C1, that's I, but C1 plus C2 plus C3, and so on. The amputation of a parallel circuit, kidney is an example again, would decrease the conductance and the total blood flow, but that would increase the total peripheral resistance. See how, whenever conductance decreases, total peripheral resistance increases. And whenever conductance decreases, blood flow decreases. They go hand in hand, they go together.